Hello everyone, myself Shubhajit. Welcome to the second video on the series of Stereochemistry. In this video, I will be discussing about transformations in two-dimensional projection formula. These transformations are very useful in solving questions that involve identification of enantiomers or diastereomers, especially in restricted rotation system. Learning this concept of transformations for the first time might be too tedious and boring because you will have to do a lot of mental manipulation of three-dimensional shapes. You might become too confused, but believe me, once you learn this concept, you can solve questions very quickly. So, if you are interested to learn this amazing concept, I request you to watch this video till the end. In case you find any difficulty in visualizing, you may pause this video and recreate the structures using pen and pencil with the help of your friend, or use online structure creating apps like the app which I have used, Molecular Constructor. Okay, now beginning with the concept. When we say that two compounds are same or different, it is implied that we are comparing from a three-dimensional perspective and we are not simply comparing the diagrams. So for us, the word same means same from a three-dimensional perspective and not the same 2D diagrams, right? So 2D diagrams are not a one-to-one mapping of the 3D structure. 3D comparison is the sure short way, but for most people, visualizing objects in 3 dimensions might be too difficult. So we have transformations that we can perform on 2D diagrams to yield the same 3D structure. The basic idea is take the mirror image and then reverse the chirality of all the chiral centers. Please note that if a compound does not have any plane of symmetry or center of symmetry, then on taking the mirror image, the chirality of all the chiral centers automatically gets reversed. So after taking mirror image, when we intentionally reverse the chirality, we are basically returning to the original compound. Let's say we only take the mirror image but do not intentionally reverse the chirality. Then we get the enantiomer of the compound, provided it has no plane of symmetry or center of symmetry. However, if the compound has plane of symmetry or center of symmetry, then on taking mirror image we get the same compound. This is because using group theory it can be proved that any structure that possesses plane of symmetry or center of symmetry can be superimposed with its mirror image. Now let me discuss some standard mirror planes. We have three standard mirror planes: vertical mirror plane, horizontal mirror plane, and the mirror plane parallel to the plane. Now let me discuss some questions which will help to increase the conceptual clarity. Let's solve this question. To solve this question, let us first transform this structure to one of its equivalent structures. So according to the rule, we have to take the mirror image and then reverse the chirality. So I am taking the mirror image about this horizontal mirror plane. So when I take the mirror image, I get this structure. Now notice that none of these carbon atoms is chiral because it is not bonded to 4 different atoms. It is bonded to only 3 atoms. So none of these two carbon atoms is chiral, and since they are not chiral, there is no meaning of reversing chirality. So this compound and this compound are the same. There is no need of reversing the chirality. This compound and this compound are the same compounds. So we could have arrived at this conclusion in some different way. Notice that this carbon atom is sp2 hybridized. This carbon atom is also sp2 hybridized. So this region is a planar region, right? So this has a planar structure. So a planar structure has a plane of symmetry, that is the plane itself. So if this compound resides in this plane, so this plane is itself the plane of symmetry. And since the compound has a plane of symmetry, so when we take the mirror image, we get the same compound. So we could have got this using this way also. Now let us solve this question. So notice that the thing that is different between these two structures is that the methyl groups are above the plane here and it is inside the plane here. So I have to bring this somehow above the plane. For that I have to perform some transformation. So let me take the mirror image about the vertical plane. That is, this is the compound. So if I consider a vertical plane like this, so the advantage is that if I take mirror image about any plane, this group will automatically get reversed. But still I am preferring this because Notice that this methyl group comes here, this one goes there, and I have to reverse the chirality. So in cyclic compounds, the way to reverse the chirality is to reverse the nature of these groups. That is, if here it is down, then in the mirror image we have to bring it to the up position, and if it is above the plane, then we have to bring it to the downward position. So you could have also got this by using the RS nomenclature, that you would write the RS configuration, same result you would get. I am doing it directly, that in cyclic compounds you have to just change the state, that if it is up you have to make it down, and if it is down then you have to make it up. So here it is down, so I am making it up. Here also it is down, I am making it up. So this compound and this compound and same are same, and this is exactly this compound which is given. So these two compounds are also the same. You might think that to convince my claim I am putting such questions, but that is not true. These questions are mentioned in standard books like the MS Chauhan book for advanced problems in organic chemistry. So these questions are given in standard organic chemistry books for JEE. So it is not that I am putting these questions by my own to prove my claim. My claim is correct, so don't judge me like that. So these questions are standard questions. It is not that I am creating these questions. Now let us solve this question. See, here the chlorine atoms are above the plane and here it is below the plane. Imagine a plane through this backbone carbon chains. That is, a plane is like this, and this group is above the plane, and one hydrogen atom which is not mentioned obviously, and that will be below the plane. So imagine a plane like this and take the mirror image about that plane. So when you take the mirror image about that plane, you must imagine it that this group will go down and this hydrogen atom will come above the plane. So these groups are going down and these groups are coming up. Sorry, means hydrogen, this group is above the plane, this is going down. This group is also above the plane, this is going down, and the hydrogen which is not mentioned is growing from down to up. So this is the thing that is happening. So we can claim that these two compounds are the mirror images of each other. Now notice that we also have a plane of symmetry, right? Notice that if we pass a plane like this that is going into the page, a plane like this, then these two halves are symmetrical with respect to each other. So since this compound has a plane of symmetry and these two are mirror images of each other, we can claim that these are essentially the same compound. So these are identical, and that is the required answer. Now let us solve to this final question. Here is the question in front of you. We have to identify the diastereomer of this compound. So if you did not know the transformation strategy which I have discussed in this video, then you might try to solve this question using RS, that is identify the configuration and then apply the similarity in RS or dissimilarity, but that will be very lengthy. See, we are given 5 options. You have to write the RS configuration for all the 5 options, and that will be very tedious and very lengthy. So we will apply the elegance of the transformation strategy. So what we will do is we will basically transform all these uh, 5 options such that we get the orientation of the keto group right. That is, when we are comparing two compounds, we must at first ensure that the orientation of the groups are right. That is, the groups are kept in the same position. Then we will check about whether the chirality is same or different. That is, whether they are above the plane or below the plane. We will check afterwards. But first we must ensure that they must be present in this order only. So notice that the keto groups are here not in the top region, so we have to bring the keto groups to the top. And one more thing that you must know, that it is very obvious, the keto group is in the plane. That is, whenever they use that is solid cone or dash, only those groups are above or below the plane, but rest of the groups are assumed to be in the plane only. So what we will do is must bring this keto group above the plane. One way you can do this, you have to look at this compound from this region. If you turn your head and put your head this side and look, then you will get the orientation of the groups right. But if you want to rely on transformation, you can rely. So what I will do is I will transform this. It is not that difficult. Transformation is also very fast. So this is the compound. Now I am cleverly choosing a mirror plane like this because I want to bring the keto group to the top region, right? else my problem will not be sorted. So to bring this to the top, I am cleverly choosing this. Now see, I will first draw out the groups or atoms that are in the plane. So I will keep them unchanged and I will draw them. And then I will reverse the chirality of the groups that are not in the plane. So this group is not in the plane, it is above. So in the after reversing, this must be below. See, when I'm reversing, I'm not getting the exact mirror image, but since I want to return to this original compound, that is why I am reversing the chirality, so that as per my rule, I have to take the mirror image and then intentionally reverse the chirality so that I get the same compound. So this one was above, I brought it below. So two groups are there, both are symmetrical, one is above, one is below, so it does not matter which one I bring to the top and which one I bring to the bottom. And here it was above and I will bring it below. So this is the compound, right? Now notice that here keto group is above, keto group is in the top of this page. This one is above the plane, we get 1 point of similarity. And notice that this group is different, that is the positioning is different. Here it is below the plane and here it is above the plane. So 1 point of similarity and 1 point of dissimilarity. So these two compounds must be different, that is they are not mirror images of each other, they are clearly entirely different compounds. So this is the diastereomer. It is done. Now we will try to solve this question. Now instead of taking transformation, we could have transformed, but there is a more shorter way, that is you look at the compound from this region. When you look at the compound from this region, you will get the positioning of the groups right. So say you look at the compound from this region. Yes, now this is the compound that you get, right? Now what we will do is we will consider a plane like this, that is if we consider this plane and we will take the mirror image about this plane. So what will happen is the groups will get reversed, this will stay at this is above the plane. So if this is above the plane, this will go below the plane. These two groups are the same groups, so if one is above, one is below, does not matter. And this is below the plane, it will come above the plane. Notice that these two structures, this structure and this structure are the same structure, so we can say that this is the enantiomer of this structure. We can find no plane of symmetry, we have only taken the mirror image and this is its mirror image. So this is the enantiomer and it is not the part of our answer, so this is not the diastereomer, hence we are not marking this option. If we analyze this option, we can take the mirror image about this region and then reverse the groups. So we must reverse the groups that are above or below the plane. When we reverse that, we get this structure. Since I am explaining, it might take some time, but when you are well acquainted with this method, you can solve very quickly. So this is the same, this is the same structure. See, we are getting the same structure, so this is same, hence it is not a part of the answer. Now notice this option. So if you look at this option from this side, it is just tilt it slightly. When you tilt it slightly, you will get that this option, sorry, this, so I have wrongly written it, please ignore it. This is the region, it is below the plane. So notice that here we are getting a point of similarity, this is down the plane, below the plane, and it is also below the plane. But here it is above the plane, it is above the plane, and here it is below the plane. So 1 point of similarity, 1 point of dissimilarity. So these two compounds can never be the same compound, they are not enantiomer, they will be clearly diastereomer. Now analyzing the fifth option, taking the mirror image and then reversing the groups, you will get something like this. So if I reverse the groups, now same thing, if you take the consider a plane like this and take its mirror image. So this group was initially above the plane, it will go below, this group was below the plane, it will come above, and we get the same compound which is mentioned. So this is the enantiomer. So the correct answer for this question is option number 1 and option number 4. Let me end this video with a caution. If you have listened to my words carefully, you must have realized that in one moment I have told that this method of transformations is most suited to restricted rotation system. There is a reason for that. My main intention to put this video was to avoid the trouble of determining the RS configuration, because it takes some time to determine RS configuration. We have to first determine the priority sequence, then the sense of rotation, then the group is above or below the plane, the lower priority group is above or below the plane. So there is a trouble in determining the RS configuration, and I wanted to avoid that trouble. That is why I put out this video. But the most appropriate method is always the RS configuration. But one thing I can guarantee is that for restricted rotation system you need not check the RS configuration. I majorly put examples where there were cyclic compounds. So cyclic compounds are always restricted rotation systems. So there you need not take the trouble of determining RS configuration. And the thing that I told was that to reverse the chirality, just reverse the groups. That is, if one group is above the plane, put it downwards. If one group is downwards, put it upwards. It is above or below the plane, just alternate. So that is a pretty sure short way, or pretty nice shortcut to solve questions. But you must be very careful when the question deals with linear compounds, that in which the carbon atoms are not restricted to rotate. That is, the carbon atoms are free to rotate. See, in this compound, the carbon atom rotates like this. So what we will get is, sorry, so let me draw this again. Yes, so this is the thing that we will get. Now observe very carefully. Here the position of chlorine changes from up to down. That is, here it is above the plane and here it was below the plane. So, but in both cases, if you write the IUPAC name or the RS configuration, it will be 2R3S. So the RS configuration remains the same, and hence it is proved that RS is the most appropriate way to solve questions when we are especially dealing with the systems where rotation is possible. The carbon atoms can rotate, especially in linear systems. So there you must always resort to RS configuration instead of checking the carbon atom, the groups are above or below, because it can be highly interconvertible. If in one case it is above, in another case it can be below. So it is always safer for linear compounds to check the RS configuration. With this, I want to conclude this video. Thank you for watching.